Wait. Hey. There we go. All right. Welcome, everybody. For those of you here, good to see you. For those of you at home, I hope all is well at home. Somebody's unmuted. I don't know who you are, but if you could all check the mute situation.
Oh, sorry, that was me.
I don't know who you were. Yeah, I still don't know who you are. Either way, we're good. Does anyone in person need a 3.1? Okie dokie. We're on 3.1. We got some more to do, quite a bit more to do in 3.1. Let's just keep trucking. So last week, I'll go back a little bit. Last week I started introducing various different types. I'm going to switch my computer here. There we go. We started talking about different types of intermolecular forces. So again, I'm going to recap the same way I recapped last week. Inter, meaning between molecules, right? Molecule 1, molecule 2, and there's a force between them. Okay, that's very different than intra, which means within the molecule. That's a covalent bond. So I've got a water molecule. Here's oxygen and hydrogen, and there's covalent bonds between the oxygens and hydrogens. That's intramolecular. Intermolecular is water molecule, attractive force between them. So we are talking about intermolecular forces. I gave you a bunch of different types. We talked about hydrogen bonding. That's going to come back today because we got more to talk about with hydrogen bonding. I'm going to just cruise back here a little bit. Right here. Okay, hydrogen bonding is an intermolecular force. It occurs when you got some hydrogen. We'll give you a bigger definition later today. The other types we talked about were London dispersion forces. London dispersion forces are very kind of abstract to explain. These are the ones that are in everything. All substances have London dispersion forces. Everything. They are the weakest type of intermolecular force, and they occur because there's random motion of electrons. And when the electrons are just randomly moving, you get these little partial charges, and then you get these tiny little attractive forces, which are called London dispersion forces. Okay. We also talked about dipole forces. What the heck's a dipole? That's not rhetorical. It's a good question, isn't it? What does that mean? When I say dipole, or when I say polar, what am I trying to say? Good, just like last week's group. I'm assuming you just don't know, maybe. Or you're just scared. Don't be scared.
Isn't it the positive region and like the negative region?
It is exactly that. Nice. Whoever talks from home, I don't know who you are, so because I don't have your pictures up, but thank you for your participation. Strange student speaking from my microphone. Yes, polar means there's a partial positive chunk or region, and there's a partial negative region. Dipole means the exact same thing. It's a molecule that has a partial positive and a partial negative somewhere. Okay? These are permanent partial charges. That's kind of the big difference between London dispersion forces and dipole forces. London dispersion forces, the ones that show up because the electrons are in constant motion, these are fleeting. They're not always hanging around. Sometimes they're there, sometimes they're not. Just through the motion of electrons, it just kind of depends. With dipole forces, these guys are always there. This partial positive and this partial negative from this example last week, those are permanent. And they're there because of these differences in electronegativity. So when you hear the word polar, when you hear the word dipole, I'm really talking about the same thing. I'm talking about something with a partial positive and a partial negative on that molecule. This little arrow down below, that's called the dipole moment. That's showing the directionality, meaning like which way the partial charges are. So the way I've drawn it here, this is pointing to the side with the negative, partial negative. And the other side of that arrow is a little positive sign to signify the partial positive. Okay? What else did we talk about? We talked about dipole-induced dipole. These are examples that have different substances. Okay, and we wrote this down as a part of that. These occur between different things. No longer like water, water, or, you know, whatever, the same stuff. We're talking about substance 1 and substance 2, and they're different, okay? And there's varying factors that affect how strong or weak these are. We went through 2 examples. In the first example, we had tellurium tetrafluoride and krypton, and tellurium tetrafluoride and xenon. And the question was, which of these is going to give us stronger intermolecular forces? The correct answer for the first one was the xenon, okay? Because, again, really the tetrafluoride stuff is the same, right? It's the same thing. So then it comes down to, well, what's the difference between krypton and xenon? Xenon's bigger. Bigger atoms, bigger molecules, they have more electrons. And the more electrons something has, the more polarizable it is. Meaning, you can move the electrons around further. You can push them. You can manipulate them to a greater extent. And as a result, you get bigger charges when you push them. Okay, you can manipulate it more. You get bigger partial charges, stronger attractive force. The second example, we kept xenon the same for both, but we switched out tellurium tetrachloride versus tellurium tetrafluoride. And now the question came down to, well, which of these 2 molecules is going to give us a stronger attractive force when paired with xenon? And it has to come down to the one with the bigger partial charges. Well, what's going to give you bigger partial charges in these molecules? The one with more electronegativity. Fluorine is more electronegative than chlorine. And as a result, these partial charges, the partial negative right here, the partial positive right there, are bigger in magnitude. They're larger numbers. And you get a stronger force. That's Coulomb's law stuff, right? Like a 10-minute recap here of life from last week. Okay. Bigger charges, stronger force. That's Coulomb's law. So, all right, where does that leave us today? Where the heck are we going? Take a look at this. Circle any bonds, and I have that in quotations, that are not covalent, and give them a proper label. Take a quick peek at this little model. Circle things that are not covalent bonds, and identify what they are. What the heck are they? Yes. You're good. Mm-hmm. What is this stuff? What is in this picture? It is. This is DNA. Or, well, at least, you know, some of the groupings of DNA, right? We have our thymine, adenine, cytosine, and guanine. Those are the DNA groups. In the middle, we have these little dotted connections. What are those? How would you describe those little connections between our 2 groupings on this page? Does anyone know?
Are those hydrogen bonds?
They are. They are hydrogen bonds. Between your DNA functional groups, you know how DNA is like the double helix thing, right? You know what holds that thing together? Hydrogen bonds. The double helix of DNA, down the center of that double helix, is nothing but hydrogen bonds holding the 2 like sides of the ladder, you could say, right? Holding it together. They are hydrogen bonds. Yeah. Let's write H bonds. Okay. They're hydrogen bonds. Is that a real bond? Is that a covalent bond? No, 'tis not. Hydrogen bonds are not the same as a covalent bond. They're much weaker. They're intermolecular forces. They happen between molecules. Covalent bonds are way the heck stronger than hydrogen bonds. Okay? All right. Now let's analyze this graph. This is going to be a chunk of time here to try to figure this thing out. Put a title on the graph. First things first, take a peek at this. Okay, you know how to title graphs, right? Nelson taught you that? Or if you didn't have 910, I'm assuming that Mr. Suey and Reed and Kramer and Johnson, Gerstenberger, Gates, they all teach that stuff. Somewhere along the line, I hope you learned how to title a graph. Maybe. How do you want to title it? Dependent versus independent. That's the foolproof way of titling your graph. Okay, here's another issue. What's dependent and what's independent? It is. Nice. Mr. Nelson will be proud. Good work. So this, we could totally call temp versus molecular weight or molar mass for our purposes, right? We've generally called it molar mass. I'm going to use that. So now that's all well and good. That's a nice systematic way of titling graphs, which you have used prior in your science life. But let me go a little bit further. What are these temperatures representing? And I'll have you focus on water, because that's the substance you're probably most familiar with. These are boiling points. These are boiling points. We know water boils at 100 degrees Celsius, right? These are boiling points. So instead of saying this, which is perfectly fine and it's systematic and it works, you could also title this as, like, you know, boiling points of various things or whatever. Okay, but these are boiling points. That's really important. Now, when you look at this graph, we have, what do we got, like 16 substances on this boiling point graph, and they're kind of clustered together. You see this bottom line? These are all like connected. The reason why those are connected is those are molecules coming from the same family. CH4, that's carbon, right? Column 4 or 14. SiH4, silicon is right underneath it. GeH4, that's right underneath that one. SnH4, that's right underneath that one. Okay, so the carbon, the silicon, the germanium, and the tin are all in the same family. If you go to the next one, NH3, PH3, ASH3, which kind of juts upward a little bit, and SbH3, N, P, AS, and SB are all in the same family, the same column. Same thing and so on and so forth for the other two. Okay, so the lines are connecting families of molecules coming from the same column for the central atom. Okay, now there's some outliers on this graph. You see how the general trend is like you go left to right, and it's just kind of a gradual increase, right? We got 3 little data points that aren't really hanging out where we would expect them based on that trend. What are the 3 outliers that we have going on here? Where's the 3 data points that aren't really fitting in with the rest of this stuff? These 3 guys, right? What are the water, HF and NH3, what are these 3 doing compared to the rest? They're not even remotely matching the rest of this data. They are very much outliers in this data set. We're going to explore what the heck's going on there. Okay? So let's talk about boiling point for just a second. The phases of matter. We've got the standard phases of matter. I'm not going to go into plasmas. But the standard phase doesn't matter, solid, liquid, gas. Okay, what makes a solid a solid? What makes a liquid a liquid? What makes a gas a gas? It has a lot to do with their intermolecular forces. Things that have strong intermolecular forces, relatively speaking, would be solids. Things with very, very weak intermolecular forces would generally be gases. So, things with higher boiling points, like water, water's got the highest boiling point on our graph here. What can we generally say about the intermolecular forces of water compared to the rest of these data points? Stronger. It takes more energy to turn water from a liquid to a gas than any of the other things on this chart. Okay? And that tells us directly information about its intermolecular forces. The forces holding water molecules together are stronger than the forces holding ammonia together, or HCl together, or whatever. Okay? That's what we're going to start looking at in this data. So, what kind of intermolecular forces do we have going on here? We've got some choices. Okay? Now, everything has London dispersion. Everything. All 16 of these molecules have London dispersion forces, because everything does. But we got to break down the other types in here as well. We're going to look at geometry just a smidge again. I know that's last unit, but we need it today. And we're going to start kind of picking and choosing what types of forces we have going on to help us explain this stuff. So this is nothing really to answer, but the criteria that must be met in order for hydrogen bonding, attractive forces, to exist between molecules is that a hydrogen must be covalently bonded to a fluorine, an oxygen, or a nitrogen, FON. What do you know about these three elements? They are the three most electronegative elements on the periodic table. That's phone, right? When we were giving Chloe a call a couple weeks ago. Bro. Okay, FON, CLBr, the five most. FON are the three highest electronegative elements on the periodic table. Hydrogen bonding.
Because it's also 3.0.
Say that again?
What about chloride? Because it's also 3.0.
Good question, because that's the same as nitrogen, right? Is that what you're seeing?
Yeah.
So for whatever reason, and I have a hunch there's a really good reason in some doctoral students' dissertation, chlorine does not form hydrogen bonds. Now, if you want me to give you a cop-out answer, I would go with that it's just a larger atom than fluorine, oxygen, and nitrogen, and therefore you don't get quite as big as partial charges, and you don't get hydrogen bonds. But the complex answer is probably more in-depth than that. So here's what I'll say. Yes, on our chart, they look like they have the same electronegativity. In reality, there's probably a subtle difference. And also in reality, there's a difference in size, which will play a factor in this too. So don't lose sleep over it, I guess. So hydrogen bonds only happen. They only happen if you have hydrogen bonded to fluorine, oxygen, and nitrogen. That is the only time hydrogen bonding can happen. Let's go back to our chart. Water, hydrogen is bonded to oxygen. HF, hydrogen is bonded to fluorine. NH3, hydrogen is bonded to nitrogen. These have hydrogen bonding. Those three substances have hydrogen bonding intermolecular forces. None of the other 13 things on this graph have hydrogen bonds. Hydrogen bonding is a stronger intermolecular force than dipole-dipole. It is a stronger intermolecular force than London dispersion. The reason why these three substances break our trend or our outliers is because they have hydrogen bonding, which is a stronger intermolecular force than all the others. Okay, and we see that. The data shows us that. They have higher boiling points. And they have higher boiling points because they have different intermolecular forces than any of the others in this set. When we go down to CH4, carbon with hydrogen, okay, there's no hydrogen bond in there. And you'll notice this is very, very weak intermolecular forces. The boiling point of methane is negative, what, 160, give or take? Because it's a gas at room temperature, right? If it's, you know, room temperature, which is like 20 whatever degrees Celsius, it exists as a gas. We're above its boiling point. Okay? All right, let's keep going. So the high electronegativity of these atoms leads to a very polar bond. When I say very polar, I mean the electrons are not even remotely shared equally, right? If you have a hydrogen bonded to a fluorine, the electrons are very much pulled towards the fluorine because of its high electronegativity. So as a result of that, okay, hydrogen bonds are strong, or sorry, as a result of that, you get hydrogen bonding. So hydrogen bonds are stronger than other dipole attractive forces. A dipole attractive force happens when you have polar molecules. A lot of these are polar. We're going to look at that in just a second. A lot of these are polar, but they don't have hydrogen bonding. So the intermolecular force that happens between polar molecules is called a dipole-dipole. It's its own separate classification. Hydrogen bonding, which is actually a type of dipole-dipole, gets its own special classification because it shows different results, unique results that we need to distinguish it separately. It's got to be a separate category. We can't call it the same thing because we see very drastically different data. Right. So if all attractive forces were equal, you might think that a lower molar mass would have a lower boiling point. Thus, we would expect that HF should have a lower boiling point than HCl. However, all attractive forces are not created equal. This is why HF is said to have hydrogen bonding rather than generic dipole-dipole. Let me break that down a little bit. I'm comparing two things. I'm comparing the molecule of HF versus HCl. Oops, I don't know why I made a bond with the first one, not in the second one. I don't know what I'm doing. I just worked. Still. A little while longer, probably. Well, they can. I don't think my job's in danger, by the way. I'm sorry. Maybe it is. I don't know. I got to watch my back. I don't know if Steph Bauer's got it out. Ask him. Do some reconnaissance for me. Steph Bauer, what do you think about browsing? That dude? I think he likes me. I don't know. All right. So these two molecules, they're linear, right? It's two atoms. You got a hydrogen, you got a fluorine, you got a hydrogen, you got a chlorine. Nothing too exciting. This one has a molar mass of, what do we get? 20. This one has a molar mass of 36.5-ish, give or take. Okay. Now, generally speaking, as molar mass goes up and you have more electrons in a molecule, you get stronger intermolecular forces because it's more polarizable. And more polarizability gives you stronger London dispersion forces. Remember, everything has London dispersion. And if all bonds were created equal, this is polar, HF is a polar molecule, HCl is a polar molecule. This one has more mass, this one has more electrons. So on the surface, that comparison seems to make the conclusion that HCl should have stronger intermolecular forces, right? They're both polar. They both would have dipole-dipole, partial negative, partial positive, partial negative, partial positive. This one's got more stuff. It's bigger. So the guess maybe would be that HCl should have a higher boiling point and have stronger intermolecular forces. But that's not what the data shows. The data shows the exact opposite. Here's HF. Here's HCl. The boiling point of HCl is much, much, much lower than HF. And the only way that we can distinguish why that's occurring is because they have different types of intermolecular forces. HCl does not have hydrogen bonds between the molecules. HF does have hydrogen bonds between the molecules. There's a difference. They kind of look like the same darn thing, or they're very close. They're very closely related, right? But the reason why this has such a much higher boiling point is because it forms hydrogen bonds, whereas this molecule does not. Okay? It's a really important distinction, hence why I'm lingering on it for a good 5 minutes. Okay, back to the chart. So, how can this chart show us that dipole-dipole attractive forces, meaning like the forces between polar molecules, how does this show us that those are stronger than London dispersion? Okay, let me pick 2 examples and we'll go through this kind of thought process as well. Let's use pH3 and SiH4. I want to use these 2 because actually, you know what? Let's use these 2. That's going to be a little easier. No, never mind. That's got hydrogen bonds. I'm going back to my original plan. By the way, none of you had me last year. When I teach, I don't come with like all my answers and all my notes. I just kind of go. And some of you might despise that with a passion because you're very organized people, like Mr. Scheidler is very organized. I'm more of a, hey, what are we doing today? Sweet, let's go for it. And anyway, so yeah, sometimes I just pick random examples to teach things from. But anyway, so let's use pH3 and SiH4. If you got a little bit of space somewhere, I would recommend you do this with me. Okay, so pH3 versus SiH4, these 2 molecules. Let's draw a Lewis diagram for pH3. Remember what those are? I'm assuming that was a joke. Yeah. Good. Yeah, let's do a Lewis diagram for pH3. I'll give you a little head start. I hope you can do that at this point in your life. I think that was maybe even on your test. I don't know if it was pH3 or ECl3. I forget. That's the Lewis diagram we should get, right? 8 electrons total. We need 3 bonds to one of each of the hydrogens. That took 6. We can't add any more electrons to the outside because hydrogen just wants the 2 from the bond. So we put the remaining 2 electrons on the middle. This is our Lewis diagram for pH3. What would the shape of this thing be? That takes more thinking, right? What's the coordination number? Let me start there. How many things are we moving or separating in 3-dimensional space? 4. We've got 3 atoms, 1 lone pair. What shape do you get for a coordination number of 4? Tetrahedral. But it's not 4 atoms, right? We've got to get rid of an atom. So I always like to get rid of the top one in my head. It's like where you got like 1 up and then you got like a little tripod. That's the tetrahedral shape. Let's get rid of the top one. What are we left with? What would we describe that shape as?
Trigonal pyramid.
Correct. The home people are on it. They're good. Thanks, guys. I think it's been a different person each time, too. This is... And I don't have the volume so loud that you scare me. I think I got a little scared last week when that happened. This is a trigonal pyramid. Okay, a trigonal pyramid. Would this be a polar or a non-polar molecule? It's not bad. Polar or non-polar? Flip a coin. You can do it. It is. It's polar. The shape of this thing doesn't allow these bonds to cancel out, right? It's not a symmetrical shape. We've got like, again, this is a little pyramid. So we'd have like 3 atoms. Here's my central atom. I would have 3 atoms underneath it, like a little tripod, and nothing on top. That's not symmetrical. I can't cancel out the pull of the electronegativities between the 3 outer atoms. This is a polar molecule. There would be a partial negative, there would be a partial positive. What type of intermolecular forces would this have if it's a polar molecule? Rhymes with schmipole, schmipole. Dipole, dipole, yes, excellent, thank you. This would have dipole-dipole intermolecular forces because it's polar. When you have polar molecules, they have dipole-dipole intermolecular forces. Let's go to the next chart. Let's go to the SiH4. If you haven't done a Lewis diagram for that, go ahead and do a Lewis diagram for that. And I apologize, I got way more space than you do because I can hit that. And so I do apologize. That probably didn't leave you enough space on your paper. There's your Lewis diagram. About as easy as life gets. Coordination number. Shape. This is tetrahedral. So now we have like 1 atom straight up from the center and 3 as a little tripod underneath it. Okay? Polar or non-polar? This is non-polar. Yeah, the tetrahedral shape is very symmetrical. Again, it's a little deceiving until you get used to it. And maybe if you jumped on that Chem Illinois website, I hope you maybe tried it. You can see that it is a symmetrical shape. It's kind of, again, deceiving at first, but this has perfect symmetry. This is nonpolar. Okay, so this is a nonpolar molecule. This up top is a polar molecule. And as a result, they're going to have different intermolecular forces. The top one, because it's polar, is going to have dipole-dipole intermolecular forces. The bottom one, because it's non-polar, will only have London dispersion and nothing else. Okay. Does the top molecule, the pH3, does that have London dispersion forces? It does. Everything does, right? But it also has dipole-dipole attractive forces. And all those different types result in different strengths. Let's go to the chart. Which of these 2 substances has a higher boiling point? Which little data point is higher up? pH3. Meaning that we would expect that pH3 should have the stronger intermolecular forces. The forces holding it together are stronger than the forces holding SiH4 together. Well, they both have London dispersion. They almost have the exact same molar mass. It's pretty darn close. Okay, silicon and phosphorus are right next to each other, right? Silicon is 28.1 on this periodic table. Phosphorus is 31. The phosphorus has 3 hydrogens with it for 3 more, up to 34. The silicon would have 4 hydrogens with it, up to 32. So there's a difference in molar mass of about like 1 gram per mole. Effectively almost the same. So they both have London dispersion. They almost have the exact same molar mass. They almost have the exact same number of electrons. I think they do have the exact same number of electrons in total. So what's the only difference? One's polar with dipole-dipole, and one is not. That is the only difference. So the whole point of this long speech was to try to analyze this statement down below. The statement was, why are dipole-dipole forces stronger than London dispersion? Well, through this comparison, by looking at pH3 and SiH4, all other factors are pretty much out the window, right? The molar mass is the same, number of electrons are the same. They both have London dispersion forces. The only difference The only difference between these two molecules, to give us some sort of indication why this one's boiling point is higher than that one's boiling point, is pH3 has dipole-dipole and SiH4 does not. So dipole-dipole attractive forces must be stronger than London dispersion forces if all other factors are equal. And that is the truth. Okay? So, do I want to say anything else there? I don't think I do. Are there any questions so far? I've been yapping for quite a while. Anything at all?
I have a question.
Go for it.
Can you, I think you already explained this, can you explain why the hydrogen bonds are stronger than other dipole-dipole bonds?
Yeah, that's a very good question. If I go back, and I kind of say it in the middle here, the hydrogen bonds end up being stronger than normal dipole-dipole because they just end up having bigger partial charges. They happen when you've got those three most electronegative elements, the fluorine, oxygen, and nitrogen. And as a result, the electrons are shared more unequally, and you get bigger partial charges in a hydrogen bond than you would in a normal dipole-dipole. So it kind of goes back to the whole Coulomb's law thing, right? Bigger charges equals stronger force. Hydrogen bonds happen and are stronger than dipole-dipole because the partial charges that happen in those bonds are bigger than normal dipole-dipole attractive forces. There's certainly more to talk about there, but I'll leave it right there. There's always more to discuss. And that's why chemistry is wonderful. Or your arch nemesis. I'm not sure. All right, so there are 4 family groups on the graph, like I kind of already pointed out to you earlier. And there are 4 members in each group. The molecules of the carbon family are CH4, SiH4, GeH4, and SnH4. Each of these molecules has a blank shape. I have symmetric or non-symmetric. I don't know if those are the appropriate terms to describe what I'm trying to describe, but I think you know what I mean. What shape would all of these have? Tetrahedral. Every single one of these is a tetrahedral shape. Is that a symmetrical shape or a... Yeah, it is, right? So all 4 of these have a symmetric shape that does not have a net dipole, meaning these are nonpolar. They don't have a partial positive or partial negative because of the nice symmetrical shape they have. The blankest boiling points on the graph are on the carbon family. Where's that carbon family hanging out on our graph? The lowest. Okay. These 4 molecules represent the lowest boiling points of this chart. Why? Because they all are nonpolar. They only have London dispersion forces and nothing else. All of the other molecules have some other type of intermolecular force going on. So the London dispersion forces, if it's the only intermolecular force there, leads to generally weak attractive forces and generally low boiling points. Boiling point is related to intermolecular forces. It takes blank to overcome attractive forces and convert a liquid into a gas. What do you need to turn a liquid into a gas? It's probably what you're thinking. Don't overthink this. Heat, aka, we'll be more generic than that, energy. Yeah, yeah. We need some energy. In the real world, yeah, what are we going to use? We're going to add some heat, right? That's how we add energy. So since molecules with no dipole have lower boiling points, remember these are the nonpolar ones, right? Then those with a dipole, we can conclude that dipole-dipole forces of attraction are generally stronger than London dispersion forces. Now, there is a big caveat to all this, okay? And we can even see it in the chart just a little bit. When you have very, very, very big molecules, that are nonpolar. There is a ton of little London dispersion forces throughout the whole molecule. And the net sum of those London dispersion forces will give you stronger intermolecular forces overall. Let me say that a different way. Wax, be familiar with wax. It's a solid at room temperature. It is a nonpolar substance. The only intermolecular forces that you have in wax are London dispersion forces. So how the heck is wax solid at room temperature with what I've told you so far? Right? Because I've been saying the whole time here, hey, London dispersion forces are wimpy, and they're the weakest, and they're low boiling points. Wax is nonpolar. Wax has nothing but London dispersion forces. It is a solid at room temperature. That's very contradictory to what I've taught you for the last half hour. Here's what's going on. Wax molecules are huge. They have upwards of thousands of carbons and hydrogens to make up one molecule. Okay? They are nonpolar, but because they are so massive, they have a ton of London dispersion forces. You can think of it like the sum of lots and lots and lots and lots and lots of London dispersion forces. Because they're so big, there's so many more opportunities for these London dispersion forces to exist. And they kind of add up over time. So if I compare a tiny molecule with a dipole, right, water is liquid at room temperature. Wax has a higher boiling point than water does. But water has hydrogen bonding, and wax has nothing but London dispersion. However, their difference in molar mass is ginormous. Water has a molar mass of 18 grams per mole. Wax has a molar mass of something in the thousands of grams per mole, or more, tens of thousands, hundreds of thousands. So as molar mass goes up, the sum of all of these London dispersion forces can have a huge effect. It's all about scale. If you have two atoms or two molecules with almost the same molar mass and everything else is equal, hydrogen bonds are the strongest, dipole are the next strongest, London dispersion forces are the weakest. But if you start looking at examples with different molar masses, all bets are off. It's much more difficult to analyze, and you got a little more digging to do. I will say that a couple times over the next weeks of this unit, because it's one of those contradictory points that sounds like I'm lying to you, and I'm not. Often, I don't generally lie to you. Sorry, that left the door wide open of me lying. When I teach you chemistry, I don't lie at all. I just sometimes don't give you the whole truth of what chemistry can be, but that's because I'm sparing you the awfulness of, like, you know, junior and senior year of college chemistry. You don't want that, unless you're going to be a chem major. Speaking of which, if anyone's going to go to Stevens Point and major in chemistry, highly specific situation. I doubt any of you are in that scenario, but in theory, if you are in that scenario, UWSP has a scholarship for incoming chem majors that I have a hunch we could do a pretty good job of getting you some money. But that implies you're going to Stevens Point, and that implies you're majoring in chemistry. So I can't imagine that applies to almost anyone. But you never know. I figured I'd throw it out there. Okay, on the x-axis, the molar mass increases to the right. We're looking at the graph still, by the way. Okay, this is still referencing that graph. The boiling point, by the way, you see this? Capital T, what's capital T mean in science? If you're doing an equation in science and you see the variable capital T, what does that represent?
Period?
Nope. What are some things that we can measure in science class that would start with a T? Temperature, that's our guy. Capital T is temp. When you have capital T with a subscript BP, what do you think the BP stands for? Boiling point. the temperature of boiling, right? So this is the symbol for boiling point. Capital T to represent temp, BP for boiling. Okay, boiling point, right? So the boiling point for the carbon family molecules increases as the mass increases. Let's go back to that graph just to make sure we're not lying. Here's the carbon family. As I go and add more mass, because again, the x-axis is mass, if I have a more massive molecule from that family, you notice that the boiling point is going up. Okay. Since the larger molecules have higher boiling points, there must be more attractive forces holding these molecules to neighboring molecules. Therefore, for large molecules, we need more energy to overcome the intermolecular forces to boil the chemical species. And as the molar mass of a family of molecules decreases, going the other way now, the electron cloud of these molecules is getting smaller. And the electrons are held more tightly, which leads to a less polarizable molecule and less London dispersion forces and a lower boiling point. Let me recap. More mass, stronger London dispersion forces. Less mass, weaker London dispersion forces. Okay? So when I go back and I look at this, you add more mass on that carbon family, and you notice the boiling point is going up. They're all nonpolar. We haven't changed the type of intermolecular force between the CH4, the SiH4, the GeH4, and the SnH4. It's the same structure, more or less. They're all tetrahedral. They're all nonpolar. What's changing? We got more stuff. That's all. There's more mass. There's more electrons. They're more polarizable. And the London dispersion forces are bigger, stronger. Still only London dispersion forces, but they're stronger, and you get a higher boiling point from as you go left to right. Okay? I'm all done. That's enough. For those of you on the internet, lovely to see you. Thank you for your participation. You guys were great. For those of you in front of my face, we'll hang out a little bit longer, and we'll pick this up tomorrow. Bye-bye, friends at home.